So this is lesson 3 in chapter 7, and today we're going to talk about the wave behavior of matter, and we are also going to start to talk about quantum mechanics. So after this lesson there is a problem set, and it will be due on Wednesday. So I cut out the first slide on accident. It's just a slide that I'm going to talk about. It talks about the wave behavior of matter, where Louis de Broglie further extended the idea of energy behaving as a particle and a wave. Any particle, whether energy or matter, can behave as a wave, according to him. We are specifically interested in electrons, where the wavelength is dependent upon its mass and velocity. So he came up with the formula lambda equals h over mv, where h is Planck's constant, m is the mass, and v is the velocity. The wavelength for most objects is so small it is not observable because their mass is so large. However, for electrons, which have incredibly small mass, their wavelengths become more important. So let's look at an example now on this next slide. At what velocity must a neutron be moving in order for it to exhibit a wavelength of 500 picometers? Well, there's a couple of things that we have to do in order to use de Broglie's equation. So first, the equation is and we are solving for velocity. So when we rearrange that, we're going to get velocity is equal to h m lambda. The second thing is that they gave us a wavelength in picometers. And we know that in order to use this equation, in order to have agreement of units, that it's got to be in meters. So we need to change picometers to meters. So we've got 500 picometers. You should always make sure that you have agreement of units. And 1 picometer is 10 to the minus 12th meters, which is going to give us 5 times 10 to the minus 10 meters for our wavelength. The second thing is you also need the mass of a neutron, which in our textbook, the mass of a neutron is 1.67 times 10 to the minus 27 kilograms. So now we can actually plug and chug on this problem. We've got 6.626 times 10 to the negative 34 joules per second. Our mass is 1.67 times 10 to the negative 34 kilogram, negative 27 kilograms. And our wavelength is 5 times 10 to minus 10th meters. And when I did the math, I wound up with 793.5 meters per second for my velocity. And so they rounded that to 794 and then put it in scientific notation. So it's the same thing. So let's look at some other examples of wave behavior of matter. On X-ray diffraction, when X-rays, which are considered to exhibit wave-like properties, are passed through a crystal, the waves are diffracted in a spectrum pattern. And this right here, I'm going to put this in a link because I can't by law embed it in the video. Go to the link. Is Rosalind Franklin's famous X-ray image of the double helix structure of DNA, which is, I don't know, I thought it was pretty cool to look at. But anyway, let's look at the following picture. So here we have an X-ray tube in the back part of the picture and a LED screen with a hole in it where you have 10,000 to 40,000 volts coming through that pinhole, which goes through a crystalline solid. And then you can see that the waves are diffracted in a spectrum pattern. So you have the initial spot in the middle from the incident beam, and then you have all these other spots around it from the diffracted X-rays, which you can see very easily on the photographic plate. So all of this information is leading up to our discussion on quantum mechanics. When similar work was done with electrons moving at a high velocity, they also produced a diffraction pattern as the waves interacted with the structure of the sample. Electrons moving as a wave and bouncing off structures as small as atoms is the basis for the electron microscope. The electron microscope can magnify things nearly 3 million times because of the wavelength of electrons is so much smaller than that of visible light, which to me is just absolutely amazing that we can do that. When electrons can be thought of to have wave-like properties, this makes it much more difficult to describe an exact location. Waves extend in space, and their location cannot be specifically defined to one particular point at a given time. So, how can we estimate the location of electrons in an atom? Can we determine where an electron is located at a particular moment in time in an atom? It's a very good question, with a very good answer. That brings us to the uncertainty principle. Werner Heisenberg proposed that there is a limitation on how much of the location and the momentum of an object at a given time. The uncertainty principle states it is impossible for us to know simultaneously both the exact momentum of the electron and its exact location in space. So he showed this through this formula, which is delta x, delta mv is greater than h, and this is supposed to be 4 pi. Where delta x is the uncertainty in a particle's position, and delta mv is the uncertainty in a particle's momentum, and h is Planck's constant. So what this showed us was that the more accurately we know a particle's position, the less accurately we know its momentum, and vice versa. Building upon Heisenberg's work and the uncertainty principle was Erwin Schrödinger, who came up with Schrödinger's equation. And this led to wave functions that describe the location of electrons in an atom. Wave functions are symbolized with the letter y. In Greek, we say psi. When y is squared, it gives us the probability distribution of an electron in an atom. Rather than knowing an exact location, Schrödinger's equation gives us regions of probability where an electron can be found. So as you see in the picture here, the intersection of the three axes represent the nucleus. This electron density distribution shows that where the more intense color is, the greater the value of y squared. There's a greater chance of finding an electron. These regions are a certain amount of energy and will also have specific shapes depending on the type of orbital, whether we're talking about S, P, D, or F, which your book shows you really nicely. So the wave functions gave rise to orbitals, each, as I said, with a specific shape and energy. This was a much different model than what Bohr had proposed for hydrogen. Remember, Bohr said that the electrons travel around the nucleus in discrete orbitals, kind of like the planets orbit the sun. Bohr proposed principal quantum number n, which corresponded with the orbits. The quantum mechanical model uses n, l, and m sub l, which is what we're going to get into now. Now I'm going to do my best to explain this to you so that you can understand it, but really the only way to get it is to memorize it and to do practice problems, which you will get after this video. So we have principal quantum numbers, n, and n can have an integral values greater than 0. So your principal quantum numbers, n, correspond to your principal energy levels. So principal energy level 1, 2, 3, 4, but they're called principal quantum numbers. As n increases, the electron density is further away from the nucleus because you're adding more shells. The size of the orbital is going to increase. And as n increases, the electron is less tightly bound, meaning because it's further from the nucleus. So the attractive forces between the protons and the electrons decrease, and therefore it has more energy. Your angular momentum azimuthal quantum number, L, refers to your sublevels and can have integral values from 0 to n minus 1. So this is our sublevels. Rather than list as numbers, they're often referred to by letter. Where S is equal to 0, P is equal to 1, D is equal to 2, and F is equal to 3. Then we have what's called magnetic quantum number, M sub L. And this actually has to do with our orbitals. M sub L is our orbitals. So you know the S has 1 orbital, the P has 3, the D has 5, and the F has 7. And this has integral values between 1 and negative 1, depending upon what your L is. So for example, a collection of orbitals with the same value of n is the electron shell. A collection of orbitals with the same value of n and L belong to the same subshell. So let's look at the example I have here. Electron orbitals with a principal number of 3 would have the following values. So principal quantum number 3 refers to principal energy level 3. Therefore, the azimuthal number can be 0, 1, or 2. Remember, L cannot be greater than n minus 1. So if 3 is n, then our greatest L can be 2. But it could be 0, 1, or 2. And that refers to, just so you know, this is the S, the P, and the D sublevels, okay, which is right here. My M sub L then refers to my orbital. So I'm going to put this again here. So this is PEL, this is sublevel, and this is orbital. Remember that the S can only have 1 orbital, so M sub L is 0. The P can have up to 3 orbitals, so we're going from negative 1, 0 to 1. So negative 1 is 1 orbital, 0 is another orbital, and 1 is the other orbital. And in D, we can go from negative 2 all the way to 2 because the D has 5 orbitals. So a couple of patterns that exist. Each shell is divided into a number of subshells equal to the principal quantum number, meaning your principal energy level. So if I'm in principal energy level 1, I have 1 sublevel. If I'm in principal energy level 2, I have 2 sublevels. If I'm in 3, I have 3, and so on. Each sublevel is divided into orbitals that increase by odd numbers. So I'm not going to talk about this screen because it just says everything that I have been talking about, and my slide did not align correctly. In the PowerPoint handout that you have, it did. So here you can see as we go from n equals 1 to n equals 4, our energy is increasing because the electrons are becoming further from the nucleus, therefore they are more loosely bound. There's not any attractive forces on them. And as they go from lower energy levels to higher energy levels, they're gaining energy. And this also is a nice chart because it tells you what your values of L refer to. Just remember that when you have the S, it has a max of first principal energy level is 2 electrons, 1 orbital. In the second principal energy level, we have a total of 8 electrons. We have 1 s orbital and 3 p orbitals. And in the third principal energy level, we have sublevels of s, p, and d, where s has 1 orbital with 2 electrons, p has 3 orbitals with a total of 6, and d has 5 orbitals with a total of 10. And when we get to the fourth principal energy level, we have the s, the p, the d, and the f, again with 2 in the s, a total of 8 in the p, 8 in the, 6 in the p and 2 in the s, for a total of 8 in the second. And then in the third level, we have your D, which has got 10, and then in your F, another of 14, so a total of 32. Okay, so we're going to end after this slide with this lesson so that you have some time to practice with all of this and the waves and frequency stuff that we previously learned. So what is the designation for a subshell with n equals 5? So n equals 5 means that it's the fifth principal energy level. L equals 1 means that we are talking about the p sublevel, because remember, L equals 0 is the S, L equals 1 is the P, L equals 2 is the D, L equals 4 is the F. How many orbitals in this subshell? Well, if it's a p subshell, we know that p has 3 orbitals, so it's going to go from -1 to +1, each of these being an orbital. So remember that an orbital, it's usually drawn like a box. Here we go. So this is the -1, the 0, and the +1. And the one thing that we didn't talk about today is, you know that there's 2 electrons in each orbital. Okay, so this is our p orbitals only. And there's another value that we haven't talked about called m sub s, and this can have a notation of +1/2 or -1/2. And this has to do with the electron spin. One is spinning counterclockwise and the other is spinning clockwise. So if I had electrons in each of these, okay, one of these would be +1/2 and the other would be -1/2 for the m sub s. All right. Problem set will be due Wednesday. And I'm actually going to record another lesson tomorrow just to get ahead.